All right, so I want to make sure everybody understands this statement here. When we talk about complex numbers include real and imaginary numbers depending on whether or not b equals 0. So when I say b, right, I'm talking about this standard form for writing a complex number. And so a is the real part, b is the imaginary part. So if b is 0, then this would be a real number. If b was not 0, then this is an imaginary number, right? So just before we list the definition out here, I just want to make sure that you understand that complex numbers include real numbers. It's just in those cases b is equal to 0. Is that clear to everybody? All right, so that being said, I want to give you the linear factorization theorem. Because this is going to help us be more specific when it comes to figuring out the number of zeros, okay? So if f of x is a polynomial of degree n, which means n is the highest power, right, on the variable, where n is greater than 0, then f, so in other words, we have to have, if n is greater than 0, we have to have at least one term that's got the x variable in it, right, or a variable in it. So then f has precisely n linear factors. So we can say f of x times some constant value a subscript n equals x minus c1, x minus c2, dot, 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 x minus cn, where c1, c2, dot, 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 cn are complex numbers. Your shirt insults me every time I see it, Diego. Because I'm trying the don't sleep thing. It's not working for me. Okay, it's not. I can't figure it out. My wife says need more coffee when you don't sleep. All right, so what does this basically mean? It means that if we've got any polynomial, now that we know about complex numbers, any polynomial, right? If I've got something that's 3x to the 4th, dot, 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 whatever, then I know, because this is the highest power, this is going to have how many zeros? 4. It's going to have 4 zeros, right? 4 zeros that are complex numbers. And like I said, that includes real numbers. So there's either going to be, there's a total of 4. They could all be imaginary. They could be a combination of real and imaginary. They could all be real, right? But now that we know about complex numbers, we know this is going to have 4 factors, okay, or 4 zeros. Does that make sense to everybody? What this definition is all about?
So that basically means there's just 4x plus or minus whatever is that making equal 0.
Say that again?
There's 4 factors of like x plus or minus blank equals,
that's right.
Makes the equation equal.
That would make it equal to 0. That's exactly right. Yep. Okay? All right, so just to kind of go through some examples so that we can put some real equations into this. If I were to give you f of x equals x minus 2, how many zeros does that have?
2. Wait.
Just has 1, right? Because this is x to the 1 power. So it's whatever the power is on, the largest power is on the x term, right? So it only has 1. And actually this one's so simple, we know what that 1 is. It's 2, right? Because that is the factor, x minus 2. If we have f of x equals x squared minus 6x plus 9, how many factors, how many zeros does that one have?
2.
It has 2. 2 zeros that are complex numbers, right? And so we could factor that and prove it, and we could say that this is x minus 3, x minus 3. So we notice with this one that we get the same 0. So we can say that the 0 is 3 with a multiplicity of what?
2.
Multiplicity of 2, right? Because it shows up twice. But notice we count it, because it shows up twice, we count that as 2 different zeros when we're applying our theorem here. Okay? So you can have one with a multiplicity of 4, right? When the highest power was 4 here, and that counts as all the zeros that proves this theorem here. All right? So you can have a multiplicity of some value. We call these repeated zeros, right? That's the term we use to define those. Now if we look at one, so x cubed plus 4x, obviously, because x cubed, because 3 is our highest power, this is going to have 3 zeros. But of the ones we've done so far, this is the first time we're going to have an imaginary zero. So if we solve for our zeros here, gives us, we pull out an x, and we get x squared plus 4. And so for this one here, if we want to figure out what all 3 zeros are, we can rewrite this middle term here to be x squared minus a negative 4. Is everybody okay with that? And why did I do that? Because now, in doing that, I've got the difference of 2 squares. If I start thinking about imaginary numbers, right? So now I have x times x minus square root of negative 4 times x plus the square root of negative 4. Everybody tracking with me so far? Steven, you're looking
I'm just wondering why.
very contemplative in the way that you're looking at the board.
Why would you put this square root on?
All right, so let's think about this. All right, that's the difference of 2 squares. So how would you factor that out?
X minus 3.
Why didn't you put 9? Why did you put 3?
It's factor of 9.
Because you took the square root of 9. Right? So when you have the difference of 2 squares, you take the square root of the term that's the second term. Well, you take the square root of both terms, actually, right?
Yeah.
That makes sense. So all I did was I took the square root of this term here. We're going to simplify it a little further, right?
And then because it's a negative under the square root sign, it's an imaginary number, right?
That's right. So I'm taking this in baby steps just so we see exactly how. Again, there's no magic in here, right? I'm showing you all of mine. I'm showing you all of the tricks. I'm showing you how you actually do it. But I'm taking it in baby steps just so that we understand it. So, so we could rewrite this piece here as the square root of 4 times the square root of negative 1. Does everybody agree that I can do that?
So then negative 1 is the I, and then the 4 is just the square root of 4, which is 2.
Which is a 2, exactly. Yeah.
Got it.
And so you'll do this enough to where you won't have to think about it this way, right? And so this would be x minus 2i, and this will be x plus 2i. And so now that I've broken it down into all of its factors, then I can say, what are my zeros for this? Well, it's going to be x equals 0 would be the first one. right? X equals 2i for the second one, and x equals negative 2i for the third one. Okay? So again, it matched what our theorem says. We got 3 zeros. It's just for this one here, we had 2 imaginary zeros, right? But that's what this definition, now that we know about complex numbers, that's what this lets us say, that we can figure out the zeros. And there's one more, there's a 4th degree polynomial example. It's the same kind of thing that we just did, but they gave us f of x equals x to the 4th minus 1. So again, we recognize that as the difference of 2 squares, and so we know that we could factor that and say that's x squared minus 1, x squared plus 1. And so we have real answers for this one, and we have imaginary answers for that one. We could break it down further and say this is x minus 1, x plus 1. And we could break this one down and say that's x minus I, x plus I. And so that's our four zeros then are 1, negative 1, I, negative I. But we get 4 since it's x to the 4th power. Okay? Alright, so let's see. I want to do some examples. I want to do the examples on page 136. Finding the zeros of a polynomial function. So we actually just did the first one actually right here. And so all I want to point out with this one, since we've already done it, is that when you look at the graph of that function, how many zeros do you see on the graph?
1.
Just 1, right? And that's because in our answer here, 2 of the zeros are imaginary, right? So we're only going to see the real numbers when we look at the graph. All right, so the graph can still help you track down your zeros, but they're only going to help you with the real zeros, right? So just be aware of that. You know, we've got a bunch of different options now. All of the stuff that we learned in the previous chapters that you took the quiz over today will help us find our zeros. We can use long division and synthetic division and stuff like that, right? So don't forget those things. We're going to continue to use those mechanisms for tracking down our zeros. So let's find, let's do example 3, which says f of x equals x to the 5th plus x cubed plus 2x squared minus 12x plus 8. And so the first thing that we do when we look at this is we say, we punch it in our graphing calculator, and we get a graph that looks like what they show in the book there. And when we look at that, one of the things that we learned about back in, and we just, again, this was something that we just briefly mentioned, and I don't even remember, it's not jumping out at me as far as seeing where that was, but like I said, we just briefly mentioned that, notice that the graph crosses, see, we're at -2, so it looks like it crosses at -2 here. And it's just kind of going up, sort of hidden from view. And then it looks like it comes back down, and when we get to 1 here, it looks like it comes back down and just touches x there at 1. And so that's something that we learned, or if you didn't get it the first time around, know this now, that if you see this happen, that does count as a 0 because it touched the x-axis. But if it only just touches it and goes back up or goes back down, depending on which direction it's coming from, that means you probably have a 0 with multiplicity of something greater than 1, right? And so we look at that and we say, specifically, this is, we may have a y-intercept of, an x-intercept of 1 here, or 1 may be a 0 with a multiplicity of 2, and then it looks like we also have potentially 2 as a 0 when we just look at the graph on our calculator. And so what that will help us do is determine some of those real zeros. So we're going to try that out. We know that our possible zeros, you just did this on the test, right? Our possible rational zeros are going to be plus or minus 8, plus or minus 4, plus or minus 2, and plus or minus 1. All over plus or minus 1. Right? And so this agrees with what we find here. Negative 2 and 1 could be a possible zero based on that. So let's try it out. And what method do you want to use to figure that out? How can we determine if negative 2 is in fact 0?
Synthetic division.
We can do synthetic division. Do we have another way?
The rational zero test.
What's that? The rational zero test?
Can you use that?
Well, what I was thinking is you could also just plug it in, right?
Yeah.
If I plug in a negative 2, if it's a 0, what should I get? 0, right? So synthetic division is definitely a path that we are going to need to go down eventually with this, but as far as a quick eyeball check, I can just look and see, does a negative 2 give me a 0 for this? And so I can plug that in my calculator. If I did that, I would find that it does, right? Now, why would I want to, if I figure that out, if I know it's a 0, and then I can check 1, and I can plug in the 1 here, and I can see, well, if I plug in 1 also, I can do that one much easier. 1 plus 1 is 2, plus 2 is 4, 4 plus 8 is 12, and 12 minus 12 is 0. So I know that 1 is a 0, but that's not going to help me figure out if it's a 1 with a multiplicity of 2. So I'm going to have to do synthetic division to actually break it down further and figure that stuff out, right? But that'll at least let me eyeball, and I'm not having to do synthetic division with multiple numbers here. Just plug them in real quick and see if I get the 0 that I think. So let's start with 2, negative 2. And when we do negative 2, we got 1. Why are we having to do synthetic division?
To break it down
Into smaller parts, right? So we can keep factoring. So that's why we're doing synthetic division. So we've got a 0 here for the fourth term, 1, 2, negative 12, 8. Did I spell that right? Okay, all right. Just panicking for a second. It's funny how many students I have that resembled this, but with like a different letter in the front. So I'm like, they're all mashing together in my mind. They're all spelled differently. Okay, so we've got this, so we're just going to bring our 1 down. 1 times negative 2 is negative 2. Bring our negative 2 down. This is going to be 4. Bring our 5 down. This is going to be negative 10. Negative 8. This is going to be positive 16. I don't know why I wrote the positive. This is going to be 4. This is going to be negative 8. And sure enough, we get 0. Right? So our next equation is going to be x to the 4th power minus 2x cubed plus 5x squared minus 8x plus 4. Right? Still not small enough for us to do factoring without doing division. So we're going to tackle the 1s now, right? So let's do synthetic division with the 1. 1 minus 2, 5 minus 8, 4. Bring our 1 down. We got 1, we got a negative 1, we've got a negative 1, we got 4, 4, negative 4, negative 4. Sure enough, that's another 0, right? So far we know that we can say that this that f of x is equal to x plus 2 times x minus 1, right? We're still breaking it down further, but we at least know that those are factors of our excuse me, of our equation. I'm just going to do this here. I'm just going to bring these down instead of rewrite the equation again. All right, and we're going to divide again by 1 because we think that it's 1 with a multiplicity of 2. So we bring our 1 down. 1 times 1 is 1. We got 0, 0. That didn't work, right? So what did I do wrong?
It does.
Huh?
It does work.
It does work. It does work. Just testing it. Just test it. All right. 4.
Yeah.
All right. There we go. 0. Okay. Did I lose anybody up to this point? Is everybody with me that we have determined now that we can break down our original polynomial into an equation that's got all of these factors times one more? What is our final factor? Well, it's not our last one, but the one we just figured out.
X squared plus 4.
X squared plus 4, exactly. Does everybody see how Adam did that magic?
Yeah, you took the bottom of the second simple equation, which is the x squared plus 4.
Right?
Yeah.
Just that's it.
And then as a factor of squares, and we know that it's x.
So that we know how to do. That's exactly what we did right here, right? We know that that breaks down into x minus 2i and x plus 2i. So we had an equation, the highest power of the x term is 5, and sure enough it has 5 zeros. 2 of those are imaginary numbers. Any questions about how I did all of that? If I gave you a problem like that, said find the zeros. And you'd be like, that would be the whole quiz, Mr. Walker, right? We're done. I'll give you this one to do at home, right? Because you guys like to take 3-hour tests, right? Yeah. But did I lose anybody? I mean, seriously, is anybody, were you confused anywhere along the way? How I tackled that problem? It's time consuming, but just kind of like a standard process to go through. So if you're confused about something, please ask it so I can clear that up now. So we don't build on that confusion. I'm just asking because I sincerely care. Questions? Okay. All right, I'm going to move on. Let's talk about conjugate pairs. So, just a note that if f of x is a polynomial with real coefficients, so no imaginary coefficients, right? They're all real numbers, only coefficients of our variables, and an a plus bi, where b does not equal 0. So in other words, the imaginary part is there, right? The imaginary part doesn't go away and just become a real number. We've got an imaginary number. If this imaginary number is a 0 of the function, then the conjugate a minus bi is also a 0. So if you know for sure that there's an imaginary number that is a 0 of your polynomial, then you know that the conjugate of that imaginary number is also a 0. Okay? So example 4 in the book says this. It says find a 4th degree polynomial. 4th degree polynomial means that the power on the highest power on my x terms is going to be 4, right? So 4th degree polynomial function with real coefficients. So that means I can use this to my advantage. I know it has real coefficients. And it has -1, -1, and 3i as zeros.
So then the fourth zero is just -3i.
The fourth zero has to be negative 3i. So there's two things that Hayden had to realize in stating that. One, this is a fourth degree polynomial. So Scott, we're missing a zero, right? I only listed 3, so there's got to be one more. And because of this rule right here, he knew that the other zero had to be the conjugate. Now remember, this particular complex number can be written like that. So when we say the conjugate of it, we're talking that, right? And so he's exactly right, but they asked us to give them the polynomial. So I'm going to have to write these factors down using these zeros and then multiply them out and figure out the polynomial, right? So what would my factors be based on these values, based on these zeros that are given here? X plus 1.
X plus 1 again.
Another x plus 1.
And then you can just do x squared plus 9 because it's a square,
Because it's a conjugate. Yeah, I could just jump straight to that, right? I could say x squared plus 9. Now, if you didn't see that, and you wrote those down as x minus 3i times x plus 3i, you're going to get the same thing, right? But it is saving a step if you recognize that. And we learned that with conjugates, right? Whenever you multiply them together, when you multiply complex numbers, you multiply 1 times the conjugate, then the imaginary terms will go away, right? And that inner term will go away as well. All right, so now this is x squared plus 2x plus 1 times x squared plus 9. So we just have to multiply each term times one another. And we would finally, when it was all said and done and we simplified, we would get this equation here. All right, that would be our f of x. Does that make sense to everybody? Now, the next example, I just want to set it up. We're not going to go through the whole thing, but this one we're finding a cubic polynomial function with real coefficients that has 2 and 1 minus I as zeros, right? And so then, since it's cubic, we know, and just because of our definition a minute ago, we know there's going to be one more zero, which is going to be what?
1 plus I.
1 plus I, yes. I'm getting really hungry, and I was just sitting here thinking about how hungry I am, so thank you for answering the question so I can continue on and distract myself a little longer. So 1 plus I, right? And so when we write down this one's a little weird because it's not as simple as this one was. And so I just wanted to show you when you write these down, you have to remember it's x minus 2, when you write them down as factors, it's x minus 2, x minus 1 minus I, and then x minus 1 plus I. Does everybody see that? It's kind of strange. But those are our zeros, right? And so what we do is we take our zeros and we say x minus that 0 is our factor, right? Just think if this wasn't this, right? If this was just the number 3, we would say our factor was x minus 3, right? And that's what we did here. We said the factor was x minus this value. And so then that's the problem that you have to multiply everything out, and they noted, and I'm sorry, I should have said this before. When we go back to our linear factorization theorem, if you guys look at that on page 135, when we wrote out the equation for f of x, when we talked about how it had all of these zeros, there there's an a term in the front there. And so we said that we could write it out as x minus c1 times x minus c2 dot 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 x minus cn, right? There is this term in the front here. And so when we're just trying to find a function that will satisfy the requirements that they gave us, we just set that equal to 1. We assume that's 1 because that would be the simplest version of it. So that's why the a isn't really coming into play for what we've done so far. But it does come into play for this one because they didn't just ask us to find a cubic polynomial function. They asked us to find a specific cubic polynomial function where if I substitute in 1 for x, I'm going to get the value 3. Okay? And so what that means is that I've written out all of my factors here, and so f of x is a times all of those factors. Okay? The a, we can't just say the a is going to be 1 because that's the simplest version. The point is there are multiple functions that will satisfy. If we just said give me a cubic polynomial with these zeros, there are multiple functions that would satisfy that because we could always take whatever we get right here and multiply it by some value in the front, and it would still give us the same zeros. Yes?
So I know it says like cubic, so there's 3, but why wouldn't you use the conjugate of 2? So like
Because that with the complex conjugate, that only applies by definition when b is not equal to 0. So you only have the complex conjugate if you've got a term that's got the I term in it. All right. So since there's no I term to this, b would be 0, right? Then it doesn't have to have a conjugate for that. All right. Good question. Does that make sense to everybody? That's why I want you to ask questions, because probably someone else was thinking that, right? That's why you ask those questions. All right, but does this make sense to everybody? The reason I'm having to leave the a in there this time is because we're trying to find a specific cubic polynomial function where if I plug in 1, it gives me 3. And so I'm going to have to figure out what this a term is this time. So I do everything that I did before, and we've got all these factors here that we would multiply out, and if we did all of that, I just don't have time to do it all, but I trust you guys. I'm confident you guys are capable enough in your multiplication skills and working with imaginary numbers that you would come up with this answer right here. All right? So this is our a cubic polynomial function, and if I set a equal to 1 right here, it would be a cubic polynomial function that has these zeros. But it wouldn't necessarily be a cubic polynomial function where if I plugged in 1, I would get 3. So that's why I'm having to figure out the value for a, because I need one specifically that will give me 3 when I plug in 1. Okay? So how do I figure that out? Well, I'm going to take this function here, and I'm basically going to plug in 1 for everything for my x terms, and what should I get over here for f of x? If I'm trying to find one that matches this, if I plug in 1 for x, what should f of x be? 3, right? So I could rewrite this and say 3 equals a times 1 cubed minus 4 times 1 squared plus 6 times 1 minus 4. Right? And so I do the math for that, and when I simplify that, I find out then that a has to be equal to -3. Because this would be what? 1 minus 4 is -3. -3 plus 6 is -3. No, it's +3. Sorry. +3. +3 minus 4 is -1. So our equation would be 3 equals a times -1. So if I solve for a, I get a equals -3. And so then my final answer for this, to find a polynomial function where a cubic polynomial function with these zeros and where f of 1 equals 3, I have to take my -3 and plug it in here. So f of x equals -3 times x cubed minus 4x squared plus 6x minus 4, and then simplify that. So I get -3x cubed plus 12x squared minus 18x plus 12. That would be my final answer. Are there any questions about that? So I want to just again set up this next example, just to make sure you understand it. Just talk through it real quick, and we'll move on to the next section. And this is example 7 in the book, and it says f of x equals x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. And we know that 1 plus 3i is 0. And so they say, find all the zeros of this function. And so if I know that 1 plus 3i is a 0, then I also know something else is a 0. I'll let you guys get caught up. What's the other thing I know is a 0?
Minus 3i.
1 minus 3i, right? So the conjugate has to also be a 0. And so the way that I would do this one, to figure out what all the zeros are, is I would say, well, that means that I could factor this guy to be I could factor this guy to be x minus 1 plus 3i times x minus 1 minus 3i. I keep stressing minus in the wrong place. It's always x minus, right? But it's 1 plus 3i, which is the first imaginary number, and then x minus its conjugate, 1 minus 3i, right? Times some unknown quadratic function that I don't have yet, right? And so if we multiplied these together, what we would get is we would get x squared. We would find out that this whole thing here is x squared minus 2x plus 10. So this times, again, some other unknown quadratic function would equal my initial function. And so now that I've figured this out, now I can use long division to divide this into that. And so when I do that, if I do x squared minus 2x plus 10 and divide it into x to the 4th minus 3x cubed minus 6x squared plus 2x minus 60, I would find out that x squared minus x plus 6 will go into that exactly with a remainder of 0. And so that is what would go in right here, x squared minus x plus 6. Or right here, x squared minus x plus 6. And so that's a really simple quadratic for me to factor, right? I can look at that and see, yeah, 2 and 3, right? After I said simple, I was like, wait a minute, is that simple? Brain cramp. So x minus 3, x plus 2 would be that, right? So those would be my factors, and so then in addition to these guys being zeros, I would know that x equals 3 and x equals negative 2 are also zeros.
Why is it minus 3 then?
Because negative 3, oh, it shouldn't be, I'm sorry.
Yeah. Because 3 and 2 both multiply, it could be...
So is this imaginary?
No, it's not.
It's not. What did I do wrong? X squared, did I write down the wrong thing? X squared, I did. This is supposed to be a negative 6.
Yeah.
So in my mind, I was like, that's the only thing that'll work, right? That's why.
Yeah.
Sorry, just copied it down incorrectly. This should have been x squared minus x minus 6. which is why I show you guys grace on the test and try to get partial credit, because there's a lot of, you just copies up and down and correct. It's really easy to make a mistake when you're doing problems that are this long. All right, any questions about how you would tackle a problem like that? So this is section 2.6. When we were looking at parent functions, do you guys remember seeing this parent function? We haven't really done any transformations with it, but do you remember what that one looks like?
Yeah.
What does it look like? It's like broken little,
Yeah, it's
right?
like two different graphs.
So it's like this guy here. You got one here, and you got one there, right? And so what we call these are hyperbolas. That's what that shape is called. That's what that graph is called. And what happens when you have hyperbolas like this, and you're going to have, it's when you've got an x term on the bottom here, right? Of a fraction. What happens in these is that you'll have these lines that the graph will approach that line, but it'll never cross those lines, right? And so in this case here, the graph, as it heads, this side of the graph, as it heads closer and closer to zero, it gets closer and closer to it, but it never actually reaches that point. And so what we call these lines here are asymptotes. So it's a line, an imaginary line there in the graph that the values are approaching, but they never actually cross. Okay? So I want to define that for you. The definition of vertical and horizontal asymptotes. There's a silent T. It's not asymptotes, it's asymptotes, is how you pronounce that. And the definition says the line x equals a is a vertical asymptote of f when as f of x approaches infinity, or f of x approaches negative infinity. That's how we read that, with a little arrow here. F of x is approaching that. Then so the line xa is a vertical asymptote of f when f of x approaches infinity, or f of x approaches negative infinity as x approaches a, either from the right or left. And so we can see that in this graph of 1 over x, right? As our x terms are approaching 0, 0 would be our a in that graph. What happens to our y values? Well, they either blow up to to positive infinity, or they head down to negative infinity, right? That's what happens here. Is it's approaching 0 from the left side. The y values go down to negative infinity. As it's approaching 0 from the right side here, then the y values go up to positive infinity. All right, so we call that line an asymptote, where they never cross it, they just approach it. And you could plug in values into this function, and you can see that as x got closer and closer to 0, that would be the case. It never quite reaches that point. Which makes sense because the graph would be undefined at that point, right? You can't have 0 for x there. You can't divide by 0. Let's talk about horizontal asymptotes. The line y equals b is a horizontal asymptote of f when f of x approaches b as x approaches infinity, or x approaches negative infinity. And again, we can just see that on our graph, right? I'm sorry, I left out something here. F of x approaches b. That's our y value. F of x is our y value. And so in this case, as our y value approaches b, we see that x, from the top and the bottom, we see that x runs to negative infinity here, and here x runs to positive infinity. So any questions about what an asymptote is? It's pretty easy to recognize if you see a graph of it, right? It kind of stands out. Again, your graphing calculators are going to be helpful as you're trying to figure these out. There's a series of graphs at the bottom of page 143, and you can see, the first one there is just it looks sort of similar to our basic inverse function. That's what we call this 1 over x function, the inverse function. But it's got both a horizontal and a vertical asymptote in that one. B only has a horizontal asymptote, right? Down there where y equals 0, it approaches that, it never crosses it. And then C only has a vertical asymptote. Oh, never mind. Y equals 0 is also horizontal. So there's a vertical asymptote at x equals 1. Okay, questions about asymptotes? So let's write down. This one's kind of long, but we need to know this definition. So sorry, I tried to figure out a shorter way to present this to you. I'm going to write it a little bit shorter than they have it in the book, but I think we're going to have to write all of this out. So vertical and horizontal. I'm going to abbreviate horizontal. I should have abbreviated vertical. Asymptotes of a rational function. So for the function f of x equals capital N of x, capital D of x, right? So we could write it as basically two polynomials over one another. And so just to kind of write that out to show what that is, that's a to the n, x to the n, plus a1 plus a0. And then on the bottom here we've got b subscript m x to the m plus b1 x. I forgot my x on my a1 term here. Plus b0. Right, so it's just showing us there's two polynomial functions, one over the other. Where n of x and d of x have no common factors. What do I mean when I say that? They have no common factors.
None of the zeros are the same.
Like I can't, yeah, none of their zeros are the same. So if I say, so if my function on top, if I were to put all these out, maybe my function on top was this, and my function on bottom was this, right? These have already been canceled out, so it's already been simplified in that fashion, right? There's no common factors. We're going to talk about what this means in just a moment. That's something, it's not called an asymptote. We've got a different name for that. That's called a hole, actually. So we're going to figure out how to find holes in your graph. But there's no common factors. Then we can say this. The graph of f the graph of f has vertical asymptotes at the zeros of d of x. So we can find the zeros for d of x for the polynomial that's on the bottom, and whatever the zeros are for that, those are going to be our vertical asymptotes. Okay? Which is exactly what we found here, right? The only zero we have for this is 0, and that's where our vertical asymptote is for f of x. I mean, for the inverse function. And then for the horizontal asymptotes, they're a little more complicated. F has, at most, one horizontal asymptote determined by comparing the degrees of n of x and d of x. So the numerator and the denominator polynomial functions. And so as we compare the degrees of those, if n is less than m, so the degree of our numerator is less than the degree of our denominator, then y equals 0, which is the x-axis, is a horizontal asymptote. If n equals m, then the line y equals an over bm, our leading coefficients, is a horizontal asymptote. And finally, the last case, if n is greater than m, so in that case there, if the degree of our numerator is greater than the degree of our denominator polynomial function, then there are no horizontal asymptotes. So, let's look at an example. Try to apply those rules. So for this one here, if f of x equals 2 over 3x squared plus 1, and it says find all the asymptotes of the graph, is what we're asked to do. For the vertical asymptotes, it's the zeros of d of x. And so if we look at d of x, 3x squared plus 1, we set that guy equal to 0. That's 3x squared equals -1, x squared equals -1/3, so x equals the square root of -1/3. Plus or minus that, right? And that's the square root of a negative number. So our answer is going to be an imaginary number, right? And so there are no real since there's no real solution, there's no vertical asymptote. Okay? If you don't get a real solution when you determine the zeros for the denominator, then there's no vertical asymptote.
And then y equals 0 is the horizontal asymptote because the numerator is greater than the denominator, right?
So the numerator, n is less than m, right?
N is less than m, right?
That's right. So because n is less than m, then y equals 0 is the horizontal. Okay? The second example, which is 2x squared over x squared minus 1. When we look at the denominator on this one and set it equal to 0, we can factor x squared minus 1 to be x plus 1, x minus 1. Right? And so that means that x equals -1 and x equals 1. If we plugged in either of these values into the denominator here, we would get division by 0, right? And so those are both vertical asymptotes. To determine the horizontal asymptote, we got n equals m, right? The degree is the same for the top and the bottom, and so we would take the horizontal asymptote is a line.
It's just 2, right?
Where y equals, what'd you say?
Just 2, right?
Just 2, right? So 2 is our leading coefficient of our highest term on the top, and 1 is the leading coefficient of the highest term on the bottom. So it would just be y equals 2. Now, I'm not going to get to section 2.7. Ugh. So hard to cover all this material because I'm looking at you guys sometimes and I'm like, they're not even processing all this because we're having to go through it so quickly, you know. So I don't know how we're going to get through all that. Let me go over this last section here for finding holes. This will just take a minute. I've already mentioned this. Well, any questions about this? Did everybody follow that? Right? If you've got the rules, it's pretty straightforward. You're going to have to know these rules, right? If you know those rules, it's pretty straightforward to apply those. And of course, you've got this handy thing called graphic calculator to check your answers, right? And make sure that it matches what you determined here. So sometimes you're going to have a scenario like this, where f of x equals x squared plus x minus 2 over x squared minus x minus 6. And so this is, we said this right here. When we're finding the vertical and horizontal asymptotes, we need to be dealing with a function where n of x and d of x has no common factors, right? But when I factor both of these guys here, I get on top x plus 2, x minus 1, and on the bottom I have x minus 3, x plus 2. Everybody agree with that? So they have a common factor, right? And so we could cancel both of these guys out, and then we could say, okay, this we can then use our rules over here for finding the vertical and the horizontal asymptotes, and they would be valid for this function. But the problem is, this was the original polynomial functions that we had, okay? And so we can't just simply discard those values, because they will have some bearing on the whole division by 0 idea, right? Because if I throw this away, but this is my original function, if I put in a negative 2 down here on the bottom, what's going to happen? I'm going to get division by 0, right? And so even though I was able to cancel those out so that I could follow my rules here, I have to remember that x cannot equal negative 2. X cannot equal negative 2, yeah, sorry. Does that make sense to everybody? You got that clear? I'm getting to know kind of when you guys are thinking, right, versus going, So we cancel these out so we can apply these rules, but we have to remember the division by 0, right? We have to remember this still applies because the actual functions that we're dealing with, this is the function that we're doing the graph of. And there's going to be a hole in the graph right here where x is equal to negative 2. All right, so it's not my asymptote because we canceled it out as a common factor. But there's going to be a hole in the graph right there. And the way that I determine the actual point where that hole is going to be is I have to plug this negative 2 in right here. And so negative 2 squared, right, minus negative 2 minus 6 gives me 4 plus 2. No, why did I do that? That's not right. I have to plug it in the whole thing. Sorry. No, I can't do that either. I have to plug it in. This is what happens when I get into a bunch of a hurry right at the end and try to squeeze the last little bit. What did they do? They set x cannot equal negative 2.
They put it into an equation form where it's just like the factors on the top and the bottom, like not in that.
Oh, they put it in here. Sorry, I got to plug it in here, right? So when I plug negative 2 in right there, yeah, it's not going to give me division by 0 when I plug it in there, but it is going to tell me where the point is on the graph that can't exist. Right? So that's going to be my hole. So I figure it out based on this that it can't be negative 2, and then I plug it in to here. So negative 2 minus 1 over negative 2 minus 3 is going to give me negative 3 over negative 5. And so my hole is going to be an x value of negative 2 and a y value of 3/5. All right. For my asymptotes, I just use this portion here, and I look at it and say my vertical asymptote is going to be what? 3. It's the denominator, right? So I'm going to have a vertical asymptote at x equals 3, and then for my horizontal asymptote, these values are the same, so it's going to be 1 over 1, right? All right, so I'm going to have to give you guys just a homework assignment for those 2 chapters. I was really hoping to finish out chapter 2 today, but You know, and it's just so short. It's just like a little bit. You guys don't mind staying for 15 more minutes. If you're as hungry as I am, you're ready for lunch. So you guys have a good day, and look out for the assignment to be posted to Google Class.